It's an honor to be presenting these Compton Lectures series. The title of my talk is Cosmic Cartography because I basically want to talk about how cosmologists today are making maps of the universe. Okay, so we're actually mapping out structure as we look back in time, okay, with telescopes. And we're also figuring out what stuff there is in the universe. Okay, and I'm going to take you through this unusual picture of what we found makes up the known composition of the universe. So I'm going to ask, if you do have any questions, can you please leave them till the end?
Can you turn it up, the volume a little louder? I'm
So
sorry.
there's no volume control. I can only move it closer.
Or move it to the other side, because when you turn to look at the screen,
Oh,
then you
that's
go
good.
toward the microphone instead of away.
Okay, how about that? Is that better?
Yeah, I think so.
Better? Okay, good. Thank you for letting me know. Okay. So if you do have any physics questions, can you please leave them to, yes? Yes, I'll turn them down, yeah. Okay. Is that good for everyone? Okay, I don't want anyone to fall asleep, so I won't turn them down too much.
Oh, they will, they will.
You haven't seen my talk yet. Okay. Okay, so yes, if you do have any questions about the slides or what I'm going through, please save them to the end because there will be lots of time for questions. Okay. Okay. So first off, I'm going to be talking about cosmology. So for those of you that don't know, what is cosmology? So basically, if you study cosmology, you're trying to figure out how the universe works. Okay. What is the stuff in the universe? And basically, what are the forces that govern how that stuff moves and interacts? And you can break down cosmology, I think, into four main areas, okay? So the first would be people who work on observations. So these are the people that actually make these measurements that we see with error bars, okay? And they are the ones that are really telling us the true universe, like what is actually out there, okay? And then you have people like me who work on the theory side, right? And they're pretty much pen and paper guys. And sometimes they forget to talk to the observational people. But it's really the observational people who are directing what's going on in the area of theory. So it's very important that we have these observations because sometimes the observations tell us that we need changes to our theory of gravity, for example. And then once you have your theory, right, once you write down the mathematical equations that you think describe observations or indeed make new predictions, then what you need to do is actually make predictions for how complex structures like galaxies and clusters of galaxies form in the universe. And in order to make these predictions now, we need n-body simulations. So we need to use computers to make these predictions. So I'll talk more about these very large computer simulations which are needed to generate accurate predictions for our theories. And then the next thing to think about is, well, maybe you have your theory that you think explains past observations, you plug it into a computer and you make new predictions for your theory. Well, then maybe you need a new survey to go out and look at a new feature in the universe to verify or falsify that theory. And this is where these surveys come in here. So really looking to the future, all these four areas tie in together and should be working together to drive science forward. So looking right back, I just wanted to take us right back to like very early maps, okay? And this is a map from the early 14th century, and this is called the Fraumura map. And you can see that this looks nothing like the globe that we know today. Okay? The continents look nothing like we know they look like today. The ratio of land to sea is nothing like we know today. But this was considered a modern map at the time when it was made. And they even went so far as not to map what they thought the Earth looked like, but what they thought were all the known elements at the time. So in the top right-hand corner here, this is meant to represent earth, air, fire, and water. So all the known elements at the time. And these are represented by the different colors here. And then they even went further than that, and they listed, well, we know our place in the actual universe. And this top left-hand corner here is the Ptolemaic system, which is meant to show the Earth at the center of the universe and everything revolving around us. Okay, so this is a very ambitious map that they made at the time, but this was cutting-edge science, okay, hundreds of years ago. So we now know, and we can smile when we look at this map and we're like, oh, we know that more things exist in the world, and we know now our place in the universe. But when you actually look at our known compositions, things get a lot more complicated, right? Now we know it's not just earth, air, fire, and water. We know that, for example, the Earth's crust is made up of a lot more things, right? A lot more complicated elements. and so is the air. So we can represent these things as pie charts, where there's a certain distribution of known elements which make up the air and the earth. And these are very familiar to us, right? And we know that these are not the fundamental elements. We know that, this is not how you break down every component of the universe. We know that there are even smaller things called atoms, and inside atoms you have protons, electrons, and quarks, even at the smaller level. So right now, we're updating our picture of what the world is made of, okay? But we're also trying to simplify that picture, and that's what particle physics is trying to do. We're still trying to make a list of all the things we know about in the universe and how they interact. But invariably, the picture gets more and more complicated the more we try to do this, okay? It gets more beautiful, I think, but it does invariably get more complicated. So if you're not happy with that, then just stick with Earth, air, fire, and water. So when we move further away from the Earth and we say, okay, well, what's all the stuff in the universe then, right? How do we make a pie chart of everything that's in the universe? Then the picture gets a lot more interesting and a lot more crazy, okay? So now all the things that we know about are only 3% of this pie chart, okay? 0.03%. These are these heavy elements. Then you can look at, well, what about stars and galaxies? We know that they make up a lot of what we see in the universe, right? Everything else is just empty space, right? But these make up 0.5% and 4% respectively. So these are really, really tiny slices of that pie. Okay. And then, well, what is the rest of the stuff that we see in the cosmos? Well, current observations all conclude that what we're looking at is 25% of the known composition of the universe is in a substance called dark matter, right? We don't know what it is. I'm going to talk about that later on. That's going to be a whole lecture in itself. And then more disturbingly, 70% of what we think the universe is made up of is this unknown energy component called dark energy. And in fact, I'm going to be contributing 2, maybe 3 lectures to talking about that in detail. Okay. So this is, it's not a very nice picture. No one wanted this picture. We would have been very happy if we could have just stopped here. But people are working really, really hard to try to understand, what is going on here, and are we even right, okay? Because we're not crazy. We're not just going to willy-nilly just accept that 70% of the universe is invisible, okay? We have good reason to think that this is true. So another very reasonable question to ask if you're, sane and you haven't worked in this area for decades, is that, well, how do you know all this dark stuff is there if you can't see it? That's a really, really good question. And one of the things I'm going to try to convince you is that if we understand the forces of nature really well, then we can infer a substance being there because of the interaction of forces with it. Okay. And I like this picture a lot. This is a picture by a Saudi Arabian artist. It's actually meant to represent the pilgrimage, the Hajj to Mecca. But these are iron filings here around a bar magnet. And for my purpose, I just wanted to say to you, we understand electromagnetism really well. Okay, so this is the force which is causing these iron filings to all line up in this swirly pattern around a magnet. Okay. So we understand this force very, very well. But imagine you couldn't see this bar magnet here, and you suddenly saw these iron filings line up like this. Then because you understand magnetism very well, you could infer that something here was interacting with these iron filings through the electromagnetic force. Okay, so it's about, even though you can't see something, if you understand the forces at play, you can infer the presence of something. Okay, and this is going to be relevant when I talk about dark matter, because we can't see dark matter. That just means it doesn't interact with light. But we can infer the presence of dark matter because we understand how gravity acts, and we can see things gravitationally respond to the presence of dark matter. Okay, so let me go back and actually outline the lectures for you. Okay, so today I'm going to talk about the expanding universe, why we think it's expanding, and then the Big Bang theory that we have for how the universe was created. Then on April 26th, I'm going to talk about mapping the dark sector. So I'm going to devote a whole lecture to talking about dark matter, what we think it is, how we know it's there, how we're looking for it currently. And then the third lecture that I'm going to be talking about will be mapping the dark sector 2, which will be talking about dark energy. How do we find out that it was there? Why do we think that it's there? Why do we know it's an energy rather than another form of matter? And then the next lecture will be, well, is it really dark energy, or do we need to modify our theory of gravity? Then I'll go on and talk about, well, if you have all these different theories for observations, current observations, how do you make predictions for a new theory? And basically what you need to do is run these simulations in very large computers. So I'll devote a whole lecture talking about how we do that. And then in the last lecture, I'll actually talk about how we're going after the footprints of dark energy. What are the characteristic signatures of different types of dark energy? How do we actually recognize those in a galaxy simulation or galaxy surveys? So you may have noticed there were some gaps in the dates there. That's because I'm going to have 3 guest lectures come in and talk to you. The first will be Tim Linden on April 12th. And Tim is an expert in looking for dark matter, okay? And he's actually doing some very exciting experiments at the moment looking for dark matter at the center of our galaxy. So he's going to come in and talk about that. Then Doug Watson. All 3 of these, I must say, are postdocs at the KICP Institute. Doug Watson's going to talk to you about how we simulate galaxies. So that's going to be a lot of how do you simulate gas actually falling into gravitational potential wells? How do you form stars? How do you make sure there's the right number of stars? All the complications involved in simulating a galaxy. And then Austin will talk to you about the very early universe. Okay, so just after the Big Bang, physics about the inflation of the universe after the Big Bang. Okay. So let me get straight on to our first lecture then. So I'm going to talk about the Big Bang theory and why we think it's true. So I like this quote from Lemaitre. George Lemaitre was a Belgian priest. He was also a professor of physics, and he described the Big Bang as a cosmic egg. And basically, we are the ashes and smoke that came out of this cosmic egg, out of the fireworks that came out of the cosmic egg. Okay, so what's the background to the Big Bang theory? How are we led to thinking that this theory is correct? So we didn't always know that the universe was expanding. In fact, when Einstein wrote down his equations of general relativity, people at the time thought that the universe was static and unchanging. Okay? And this was kind of an appealing view that the heavens were just this static sphere that we looked out upon. Okay? And this is something that Einstein himself thought to be true. So when he wrote down his equations of general relativity, okay, his theory of gravity, he actually tried to make the solutions to that theory agree with a static universe. But the reality is that his theory actually predicted a dynamic expanding universe. Okay. And this picture here shows Einstein here and De Sitter. At the time they were arguing over the solutions to Einstein's theory of general relativity because De Sitter came up with a solution which did give an expanding universe. But in fact his theory had no matter in it, so it couldn't possibly be the correct theory for our universe, which was unfortunate. And Einstein was still stuck to his guns and he wanted a static, unchanging solution. So obviously theorists can argue all day, but it's up to observations to really tell us what is the true answer. And then in 1923, Edwin Hubble, who actually is an alum of the University of Chicago, he did his degree here at the university, he made observations of galaxies at different distances from the Earth. And what he was measuring was their velocity at different distances from us. And what Hubble measured was this tight relationship between the recessional velocity here, given in kilometers per second, and the distance that a galaxy is from us. Okay, so this is given in these strange astronomical units, megaparsecs. So this is 10 to the 6 parsecs. You can think of a parsec as the time it takes light to travel. Light travels a parsec in about 3 years. Okay, so these are really, really large distances from us. But we can make these observations of the recessional velocities of the galaxies as a function of their distance to us. And what Hubble found was this linear relationship between the two. So what does this tell us? It tells us that the further away a galaxy is from us, the faster it's traveling away from us. Okay. So you get this picture that everything is expanding away from us. And you might start thinking, well, are we just in a really unpopular place in the universe? Everything's just kind of away from us. But that's not true, right? So what we think is that we're not in a special place in the universe, that actually things are expanding. If you were at any other point in the universe, you would see the same thing, okay? That expansion is happening all around the point that you observe. So Hubble's data that I showed on the previous slide here, this was data taken in 1929. So you can see there's very few points here, so you might think, well, why do I believe that? There's only a handful of points. But we have modern measurements. I mean, this is from 1998, so not so modern. I probably should have showed you a better plot going out to further distances, but you can see that this relationship is very tight here. So the scatter on these points is very small, The theory line is this solid black line here. And this is showing this relationship between the velocity and distance, which can be expressed in this equation here. So this is just saying that the velocity is equal to a constant times the distance from us. And we call this constant Hubble's constant. And we've measured it to be about 70 kilometers per second per megaparsec today. So this constant here tells us the expansion rate of the universe. So we have this notion that galaxies are moving, the further a galaxy is away from us, the more faster it's moving away from us, okay? How does this fit in with Einstein's theory of general relativity? So in Einstein's theory of general relativity, that theory tells us that the expansion of the universe, okay, so how things move in the universe is related to stuff in the universe, matter in the universe, matter and energy. So how the universe is expanding is also related to all the things in the universe as well, the matter and the energy. Okay. And one of the solutions to general relativity is the Friedmann equation, which I've kind of written here in a simplified half maths, half English way. So now the Hubble parameter is written here as this h0 squared value. This is Hubble's constant, so you can just think of that as a single number. But as we go further back in time, you could imagine that the expansion rate of the universe actually changes. Okay? And it changes because the density of these different components change over time. So think about all the stuff there is in the universe. Well, we know there's matter because we see matter around us. We know there's radiation. So when I talk about radiation, I'm talking about photons, for example, light particles. And then curvature, I'll talk about a little bit next in the next lecture. Curvature, I'm talking about curvature of the actual universe. So is the universe flat? Is it curved like a sphere? Or is it maybe a different shape like a saddle shaped in an unusual way? So all of these things actually sum up and give rise to the expansion rate of the universe. So this is something that Einstein's theory of general relativity tells us. So if we know the stuff in the universe, if we're accurate in measuring this side of the equation, we can actually predict what this side of the equation is. We can also measure this side of the equation and compare with our prediction. Okay. So if we have this idea that the universe is expanding, how do we even think about this, right? So if the universe is expanding today, things are moving further and further apart. If you roll the clock backwards, then surely things were closer and closer together. Okay? You roll the clock backwards even further, and suddenly all these galaxies and stars that we see start to pile up on one another. So this is this idea of when you take the fact that we're expanding today and that the expansion rate is changing over time, and you roll the clock backwards, you end up with this idea of a Big Bang, okay, that we had to have started from not a point, but there had to have been some singularity where all space and time suddenly came into existence. So this analogy of blowing up a balloon, and when you think about the expansion of space-time, really that the galaxies are just moving further away from one another. The galaxies themselves are not expanding. So this analogy of taking a balloon and blowing it up is not perfect because obviously there's no one point that the universe is expanding from. We think that each point is expanding away from every other point. But this analogy is quite good because if you were to imagine this balloon here, you could place on the balloon tiny little ants, okay, which are meant to represent these galaxies. And as you blow up the balloon, the ants get further and further apart. Okay. The ants themselves don't start expanding. Okay. And that's an important point in this analogy because the galaxies themselves don't expand as the universe expands. The galaxies are gravitationally bound systems. Okay. So they have actually, we call it decoupled from the expansion rate. They don't really care too much about the expansion rate, so they stay together as a galaxy. The space in between the galaxies does change and does increase. So why did I say ant instead of just saying some point on the balloon as it's blowing up? Because ants can actually walk independently of the rate you're blowing up the balloon. And that also represents what happens to galaxies. Galaxies have their own intrinsic velocities, their own built-in velocities where they can move independently of the expansion of the universe. So this analogy, as I said, is not perfect. But you can think about it like this, that the galaxies themselves don't expand in the same way that ants on the balloon don't, and the ants can actually walk around. So this leads to complications when you're trying to measure the expansion rate of the universe. Well, we try to measure it by observing these galaxies, and then you have this complication, well, that galaxies are detached from the actual Hubble flow, the expansion of the universe. But also, these galaxies have their own intrinsic motions. Okay? They're moving independently of the expansion of the universe. One of the really cool things is that as the universe expands, the wavelength of light actually gets stretched. So how we make...
The light gets what?
Stretched.
Oh,
Yeah.
okay.
So all of the observations that we make in astronomy use light. Okay, so that really is our medium for seeing stuff in the universe. So the fact that light, the wavelength of light gets stretched is very important, and it's something that we have to account for when we make measurements in cosmology. So let me talk a little bit about the electromagnetic spectrum for people who are not familiar with this. So when I mention light, what we really mean is the full electromagnetic spectrum. And the part of that spectrum that we're just used to seeing is this visible range here, okay? Just the everyday colors that we're familiar with, plotted down here. But there's a whole different range of light which astronomers use to make observations in different wavelengths, okay? So there may be the radio wavelength, the microwave, which you're familiar with just for cooking food, right down to the gamma ray. Part of the electromagnetic spectrum. Okay. And each part of this spectrum can be used to make observations of things in the universe. Okay. And the fact that we just see a small part of it means that just every day we're missing out on seeing things in all these other bands, but astronomers can build instruments which take advantage of these different bands. And it means we can make observations in these different bands. So not all humans are restricted to just seeing in the visible range. So there have been reports of people seeing in the UV. Monet was one famous example. So this is the same painting taken before and after cataract surgery. So it's a lot of people who have cataract surgery after report being able to see in the UV. And they all consistently report a blue wash over everything. And Monet's later paintings all have this blue wash. Okay, so just to show you how we use these different wavelengths in astronomy, things you may be very familiar with looking at look very different when you view them through these different wavelength glasses. So you may be familiar if you've ever looked up at the night sky and you're not in a city, so you don't have basically the interference due to the lights in cities. You may have seen the actual band of the Milky Way. And in our visible range, it just looks like a dusty band here because there is a lot of dust in the Milky Way. So this is actually blocking the light coming towards us. If we were able to put on X-ray glasses, we would see a very different picture down here. So now you're actually able to see more structure inside the Milky Way. And in the radio, it looks very different, very alien to our eyes indeed. Okay. So when astronomers make pictures, a lot of pictures that you will see coming from if you're on the astronomy picture of the day website, a lot of these pictures are actually composites of different bands. Okay, so they're different bands added together, which build up a picture of what the full structure looks like. And different instruments are built in order to take advantage of these different bands. Okay, so it's not just one instrument which makes these measurements. Okay, so the wavelength of light is very important for making observations in cosmology and in astronomy. So we need to take into account the fact that light gets stretched by the expansion of space. So this notion that the wavelength of light gets changed may be familiar to you if you've heard of this Doppler shift. So if you think of an ambulance, everyone's used to hearing an ambulance just going around on the street. When the ambulance is coming towards you, you hear the intensity increase, okay, as the ambulance is coming towards you. And as it goes away, the intensity suddenly drops off very, very quickly. And this is called the Doppler shift. And that Doppler shift is happening to the sound waves, but it's a similar effect with the wavelength of light. So as something is moving towards you, the wavefronts of the light actually pile up, and if something is moving towards you, that object, we say it is blue shifted. If the object is moving away from you, the wavelength gets stretched, and we say it is red shifted. So this is the Doppler shift of light. The fact that space is expanding causes a different stretching on top of this Doppler shift. So you remember I said that galaxies are moving, they have an intrinsic motion on top of the expansion of space. So that intrinsic motion causes a Doppler shift, and then the fact that space is expanding causes a separate stretching of the light. The expansion of space always causes a red shift, okay? But the Doppler shift of light causes a blue shift if the galaxy is rotating, for example. The part of the galaxy that is moving towards you, you will see blue shifted. The part that is moving away, you will see red shifted. Okay? So we understand these two differences very well. And this is how we make our measurements of distances in the universe, okay? Looking at absorption lines from our sun, for example, so all these different colors coming from our sun. We can put these lines down, and we know the distance to our sun, and then if we look at an object which is further away, so for example, a cluster of galaxies at a distance of 1 billion light years, we can see these lines which we can calibrate from our sun have shifted to a new position. Okay? And this is how we measure the distances. So I may talk about the red shift of an object, and by that I mean the distance from us, okay, because that's how we measure distances. Okay. So back to this idea of if everything is expanding away from us today, and we roll the clock backwards, then everything starts to pile up until everything is on top of one another, and we're left with this notion of a Big Bang. Okay, so a Big Bang is a singularity. What that basically means is that our equations of physics break down and we don't know what's going on. Okay, so that's basically what a singularity is. We can't talk about, I mean, people have theories about what happened before the Big Bang or at the moment of the Big Bang, but none of those have, you know, it's very, very difficult to prove those theories at the moment. So all we can really talk about is just after the Big Bang, we were in a state of infinite density and temperature, okay, and everything expanded from there. And right down at the very beginning here, you're looking at a soup of material, very hot, very dense material that actually cooled and expanded and clumped together under gravity to form the galaxies that we see today. So the reason I had a picture of Gamow there is that one of the predictions of the Big Bang theory is about the origin of the chemical elements. Okay, so the primordial elements that existed at the very beginning here in this hot, dense soup straight after the Big Bang, the abundance of elements like hydrogen and helium, you can actually make predictions for the abundance of these elements and the abundance that we see today in the universe. And this is something that George Gamow did and showed that within the Big Bang theory, you can actually explain the abundances of primordial elements like hydrogen and helium. Okay, so the Big Bang theory is basically saying that the universe started from a singularity, which gave rise to a hot, dense state, which has since expanded. So how do we know that this theory is right? There's several observational successes of this theory which are really, really impressive and very hard to replicate with any other theory for how the universe started and how it was created. So first off is the expansion of the universe. Right? It's hard to have another theory which explains the observations of the expansion of the universe if you roll the clock backwards. The second thing is the age of galaxies. So given the actual expansion of the universe, you roll the clock backwards towards that point which you think was the Big Bang, right? You have to allow enough time for galaxies to form and for those observations to agree with the ages of the oldest galaxies that we observe. Okay? So those two things fit in together. The time that the universe has been expanding for, and then the age of the oldest galaxies that we see. The third thing is the abundance of light elements. Okay, so I'm not actually going to talk about this today because this is quite involved. So this is, on the previous slide I mentioned George Gamow's work, calculating, well, if you have the very first elements that were formed after protons and neutrons combined in the early universe, you start forming things like hydrogen and helium. And we know that those primordial elements then, as stars and galaxies start to form, stars actually burn and combine these light elements and form heavier elements. Okay? So these are stars, you can think of them as furnaces which generate heavier elements from light elements. And then there is a certain population of light elements left in the universe, and we know that these must be left over from the Big Bang. So it's these abundance of light elements which what we measure today agrees with what we predict from the Big Bang theory, what must have been produced in the early universe. The very last thing here, the observational success of the Big Bang theory, is the one I'm going to focus on the most, and has been the most important discovery, really, in cosmology. And this is the cosmic microwave background. Okay, so this cartoon here is meant to show all the different stages of our universe. So when it started right back at the Big Bang in this flash of light here, We then think that the universe expanded in a period called inflation, which I will not be talking about in these lectures. That's a whole other lecture series in itself. So this period of very rapid expansion, okay, and in this period of very rapid expansion, you still have this hot, dense soup of material. Okay? And then as the universe expands, it cools. Okay? Things get further and further away from one another, and these protons and neutrons, which are combining and forming elements, the light elements, are stable elements, then you no longer have free electrons which interact with the light. Okay? So when you have a hot, dense soup of material and you have free electrons, the light particles are bouncing off these free electrons. Okay? So it's like light being trapped inside a cloud, and the light is not able to get out. But as the universe expands and cools, these electrons combine with protons, and what you then get is the light is able to stream through these neutral particles. Okay? So the light is no longer trapped inside a dense medium. And once the light is able to free stream out of this dense soup of material, that is the formation of the cosmic microwave background. So the cosmic microwave background is the first time the light from the Big Bang, these photons, get free from the hot plasma. And basically, once it is released from the hot plasma, it just streams through the universe until we measure it today. So this is really the first light from the Big Bang. So this is why people talk about the cosmic microwave background as the oldest light that we can observe in the universe. Okay, so just to go through that a little bit more in case you're confused about how the Big Bang was made, or sorry, how the cosmic microwave background was made. So in this picture here, you have this notion of a Big Bang singularity, okay, and then a period of very rapid expansion called inflation. But right down here, now you're in this era of this hot, dense soup of material. So you have free electrons and protons and the radiation. Okay. Once you start to get light elements forming, the light is free then. Okay, and it's able to just free stream through the particles, and it no longer scatters off electrons. Okay. And this is why we call this surface here the last scattering surface. It's the last time that the light actually scatters off particles, and then it free streams through the universe onto us. So a certain number of these cosmic microwave background photons, or CMB photons, do actually get lost inside galaxies and clusters of galaxies. So these are secondary effects to the things that we measure. But many, many of these photons just reach us without having actually been disrupted on their way. So we're able to make very precise measurements of this last scattering surface, which actually happened about 380,000 years after the Big Bang. So the analogy with looking up at the sky here and seeing some clouds is similar, right? There's lots of light particles inside the cloud which are bouncing around and getting scattered. And then the surface of the cloud here is the last time that the light gets scattered inside the cloud, and then the light particles just travel straight through our eye. So we're able to see the structure of the cloud here, because that's how the particles, once the particles leave the cloud, the light particles still give us information about the structure, the surface of that cloud. So one of the key predictions of the Big Bang theory for this leftover radiation is that the temperature of the cosmic microwave background should be about 3 Kelvin. So this is 3 degrees above absolute zero, so very, very cold. So this is within the Big Bang theory, we can actually make a prediction for, well, at the time it was produced, within the theory of the Big Bang, what was the temperature of this radiation? And it was really, really hot at the time it was produced. It was 3,000 Kelvin. But we know that as light travels through an expanding universe, the wavelength of that light gets stretched. And when you stretch the wavelength of light, you cool down its temperature. Okay? It loses energy. And so the expansion of the universe actually shifts the radiation to colder temperatures. So this is why we measure a temperature of 3 Kelvin today rather than 3,000 Kelvin. And we should also be really fortunate that the temperature of the cosmic microwave background is not 3,000 Kelvin. So, okay, so this is one of the key predictions of the Big Bang theory, is this notion of if the Big Bang theory is correct, if we make a calculation of all the light elements that were around at that time, the photons that were interacting with them, when the cosmic microwave background was produced, when the light got free of those particles, if the universe is expanding, the light moves through it and the wavelength gets stretched, we can make predictions for each stages of that. Okay? And we come up with this number of 3 Kelvin. Right? So there's a lot of assumptions going in there. Right? There's a lot of assumptions about physics that happened billions of years ago, and yet we expect this prediction to be correct. And the amazing thing is that we have measured it to be correct. So let me talk about the history of measuring the cosmic microwave background. So the cosmic microwave background was discovered, measured in 1965, but the fact is it could have been discovered in 1940, 20 years earlier. And I didn't know this until a couple of weeks ago when I was researching for this lecture. So I wanted to add this in because I found it very interesting. We could be 20 years ahead in cosmology. So it was actually an observer called McCallum who measured a rotational temperature in a CN molecule in interstellar space of about 2.3 Kelvin. Okay? And just didn't assign any cosmological significance to it, but just noted it down as being a background that he measured. And then at the time, there were lots of different theorists who were arguing over the validity of the Big Bang theory, whether or not this theory was true. And one of them was Fred Hoyle. Okay? And he was actually an opponent of the Big Bang theory. He preferred the steady state idea. And he actually coined the phrase Big Bang theory in order to mock the theory. Okay? He thought that this would ridicule it, giving it this name. So it just stuck. And he actually wrote a review of the Big Bang theory in 1950. Fred Hoyle was aware of Mackellar's measurements. He noted the measurements in the review, but he actually overlooked the connection between Mackellar's observations and the prediction of Big Bang theory of a temperature which should be in the range 1 to 5 Kelvin. So the fact is that there were 2 radio astronomers who were working at Bell Labs. They were called Penzias and Wilson. And they were doing a separate experiment. Okay? They were not cosmologists. They were not interested in the Big Bang theory. But they noticed that no matter where they pointed their telescope, they were trying to calibrate the noise signal in their telescope. No matter where they pointed their telescope, they measured this background signal, okay, which was about 3 Kelvin. And the interesting thing is, they were really puzzled because no matter which way they pointed their telescope, they measured the same signal. And this was even after they cleared out some pigeons which had been roosting in the telescope, which they thought were responsible. So the funny thing is that they were not working on the Big Bang theory or anything like it, but they had actually discovered the cosmic microwave background. So this is what their measurement looked like. So this is not a PowerPoint oval. This is actual data. And this is showing you that the spectrum, the temperature spectrum, is the same everywhere you look. And this is very hard to get, right? This is uniformity that you don't measure anywhere else in the universe. So what does this oval mean? This is basically, if we're looking out into the sky, everything we see around us appears as a sphere. Okay, now you're taking that sphere and peeling it back, and this is how you get these familiar ovals that people see. So this 3 Kelvin signal, which exists everywhere and is very uniform, we can actually see it ourselves. So if you have an old analog TV, you can see a certain amount of this static when you tune in between channels is responsible due to the CMB, the cosmic microwave background. Okay, so with the switch to cable, we no longer are able to tune into the CMB channel. Okay, so the fact that we do measure this 3 Kelvin signal, which is the same everywhere in the sky, is telling us that the cosmic microwave background is remarkably uniform. Okay, and if we try to look for variations in this signal away from that 3 Kelvin signal, the perturbations are actually tiny. So you're talking about perturbations of 1 part in 100,000. So these are very, very small changes. And the fact that the CMB is remarkably uniform is telling us something very fundamental about our universe. It's telling us that our universe is isotropic and homogeneous. So this is telling us no matter where we are in the universe, things look the same, and they also look the same in any direction that we choose to look in. So just an example here of a situation where you could imagine a universe which is isotropic but not homogeneous. Imagine the Earth was sitting at the center of this sphere here. Everywhere we looked, it would look the same in every direction. Right? But clearly this is not a homogeneous universe. If you lived out here, right, this is a very different environment to if you lived in the red circle here. So this is this notion of you could have a universe which is isotropic and not homogeneous. And then on the other hand, you could also live in a universe which is homogeneous but not isotropic. So this is a notion here of imagine you had a vector field. So if you think about wind currents on the Earth, okay, at every point in space there's a magnitude for the wind, but also the direction which the wind is blowing. We call that a vector field. Imagine that all these arrows were the same magnitude and pointing in the same direction. Then that would represent a situation where things are homogeneous but not isotropic. There's a definite preferred direction for things here. But this is not what the CMB is telling us. The CMB is telling us that we live in an isotropic and homogeneous universe. So these perturbations that I was talking about here are very, very small, but we've actually measured them. So moving on from what Penzias and Wilson measured, the next satellite we sent up to measure the CMB was called the COBE satellite, which was sent up and made these measurements in 1990. And these are the measurements of these tiny perturbations. So these are perturbations at the level of 1 in 100,000. Okay? So if you take away that 3 Kelvin signal and you look for tiny variations in that signal, this is what you find. So you can consider this the universe's baby picture. Okay? This is the oldest light that has come from after the Big Bang. We can actually go a bit further and look at more modern measurements of the cosmic microwave background. So this is results from the Wilkinson microwave anisotropy probe. So these measurements were made in 2001. And you can really see how much, just improving the detector, we've been able to improve our resolution here. So what are these blue and red and yellow spots? Basically, these are temperature variations. Okay? So what you're seeing here are hot and cold spots in the very early universe. So these measurements are of the temperature of the light, which has traveled from just after the Big Bang until today. And it's showing us basically the surface of that cloud. Okay? So if you think back to the image of someone looking up at the sky, this is showing us the detail that existed in the plasma just after the Big Bang. These are temperature variations. So what are these temperature variations caused by? They're caused by density perturbations in the early universe. So basically matter clumping and oscillating in the early universe caused these differences in the temperature in the light. And then bringing you right up until today, our most modern measurements are from the Planck satellite, which were made last year, released last year. Planck is still releasing data at the moment. And this is showing your increase in resolution in these hot and cold spots. So we're really, really zooming in now on these hot and cold spots and able to make much, much better measurements of what's going on. So just to compare, put them side by side, the resolution of the 3 satellites, how far we've come since measurements made in 1990 right up until 2013. Okay, so this increase in the resolution really allows us to pin down the physics of the early universe. Okay, all the things that we think went on in the early universe, now our error bars are getting much, much smaller, and our theory is being confirmed to very high accuracy. So I just want to show a short video here of how we actually make these maps. Hopefully this will work. Okay, so this cartoon here is meant to represent our Milky Way galaxy. So we're just zooming in on the Milky Way. And we think the Earth lives in one of the outer spiral arms. So this is the Earth here with our sun. And then imagine you place a grid for reference on all the things that we see around us. Now you're going to peel back the surface of everything we see around us, and now you see the band of the Milky Way. So now what we're doing is just going through all those different electromagnetic spectrum, okay, right up until we hit the microwave range. And this is what COBE saw. And now what we're doing is turning up the contrast, so we get right down to those variations, okay, which are 1 part in 10 to the 5. So this is basically how we make these maps. Right down at very low contrast, we see just that one color oval, which is what COBE saw. And then when we turn up the contrast, we're able to see these very, very small deviations from uniformity, which is where all the physics are. So what do these hot and cold spots tell us? Well, there's just so much information in these hot and cold spots. I'm just going to focus on one, which is the size of the hot and cold spots. Okay, so what you could actually do is go around this map of the CMB and measure, well, what are the sizes of all the different hot spots and cold spots, so the red and blue spots, measure the size of those spots and count the number of them. Okay. And you might say, well, I would expect an equal number of each, for example, just being totally unbiased. but there's actually a distribution associated with the sizes and the numbers of these spots, which tells us about the density variations in the early universe. They're telling us about how matter was clumping in the early universe, and also how this plasma in the early universe was oscillating. So what we're actually doing when we count these temperature differences of different sizes, we're actually looking at oscillations in the fluid which existed in the very early universe. So if we go right back again and we think about this hot, dense plasma, gravity caused pockets of high-density matter to contract. And before the CMB was produced, the light particles, the photons and the matter were intertwined. Okay, they were just moving and sloshing about like a plasma. And because you have electron pressure there, okay, you have radiation pressure in that plasma, which is resisting the pull of gravity. Okay? And so what you get is this oscillation in the cosmic fluid. So you get this real sloshing around, but you also get a coherent sloshing. So you get some actual fundamental modes and then overtones of the modes. So the analogy with music is actually quite apt. You really do have a fundamental mode of oscillation of the plasma, and then other modes which we can measure. So once the CMB light is released from the plasma, once the cosmic microwave background is produced, it still bears the signature of these overtones and of the fundamental mode. So the cosmic microwave background has been imprinted with these wiggles. And what we measure here are wiggles that look like this. So this is just measuring the size of those hot and cold spots, the angular size of those, and we're just basically measuring the number of those. Okay? And what you can see is that we predominantly are dominated by hot and cold spots of a very particular size, so 1 degree. Okay? So you can think about that as twice the size of the full moon. So this is a scale which is really dominant in the hot and cold spots. So that's telling us about this fundamental mode of the oscillation of the plasma. Okay? And that's telling us something fundamental about how that plasma was moving and the interaction between the gravity and the radiation pressure in that fluid. So it's very hard to go into it, but just believe me when I say there's a huge amount of physics which goes into describing the size, the position, and the relative heights of these peaks. So the red points here are the measured sizes, the measured temperature fluctuations. This green line here is not a fit to those points. It's actually the theoretical prediction. And we have impressive measurements which go down to even smaller scales, smaller temperature variation sizes, okay, where our measurements are just agreeing with the data in a way which is spectacular. So there's a huge amount of physics which goes into understanding all of the temperature differences which you see in the cosmic microwave background. So I'm going to wrap up there. But before I do, I just want to say that many of you may have questions about the recent discovery, which was in a lot of the newspapers. So it was actually on the front cover of the New York Times with a picture of Alan Guth, who was one of the theorists who proposed the theory of inflation. So basically, I'm not going to talk about this discovery today. We're going to devote a whole lecture to it in about 2 weeks' time. But it is very, very exciting. It's another signature of physics in the very early universe which has been detected. And it's a whole other lecture in itself. So if you do have any other questions about this, I recommend you leave it until a couple of weeks' time. So the last thing to say is that next week we're going to have a guest lecture, Tim Linden, who will be talking about his work on detecting dark matter from the center of the galaxy. So thank you very much.
When you refer to the early universe, is that the first 380,000 years?
Sorry, say that again?
When you refer to the early universe, does that refer to the first 380,000 years?
Yes, it does generally. Yeah.
And then the cosmic microwave background is.
So no, you would consider the cosmic microwave background as the early universe as well. There's no hard, fast limit on when people say the early universe. Yes, sorry, you were saying?
Isn't the Big Bang Theory partially successful because of the series of hot add-ons and not the original theory. What I mean by that is, first of all, Big Bang theory did not have the accelerating expansion of the universe. That came later with dark energy. It seems to me the original Big Bang theory didn't work until it had the ad hoc add-on of inflationary theory, for which there's not a clear physical explanation, but without which the Big Bang theory wouldn't work. So that it's been more of a series of modifications, is what I'm saying, that have allowed it to work as a theory as opposed to an original clear theory.
So when you take, so it's true that you do need inflation in order to explain observations in our current universe, okay? But it's not that, I mean, the Big Bang theory, it's not that dark energy had anything to do with the Big Bang theory. Dark energy is very, very separate to that, okay? It fits in with the theory, but we'll talk about dark energy later. Just the measurements of the expanding universe was the first thing that pointed us to the fact that the universe is unchanging and is not static. Okay? And once you're faced with that reality, and then you turn the clock backwards, then you are looking right back to the early universe, and then you're faced with this notion that things start to pile up on one another. Okay? So it is a case that observations prompted us to take the Big Bang theory seriously, but I wouldn't say it's ad hoc add-ons that make us believe the Big Bang theory. There are lots of other questions, so maybe save it till after.
Thank you.
Yes, Glenn?
Talking about the ants on the surface of the balloon, I'm a little troubled as to why they aren't also expanding. I understand they may be overwhelmed by other forces, but is there a component of expansion just being overwhelmed, or do they not expand at all?
They don't expand at all.
Okay.
So, So if you're talking about galaxies,
or ants, or me,
galaxies or ants. So it's all about the relative scales of things. Okay. So if you're talking about the range of forces and where you're affected by forces, it really, you need to be aware of the scale of things. So a magnet in a laboratory in Europe is not affecting you right now. Okay. So the scale of that force really doesn't affect you. Okay. And when you think about a galaxy, and it forms because of its gravitational attraction to one another, and things fall together, okay, and the attraction is causes things to clump together. That force of gravity overwhelms the force of the expansion of the universe. So the expansion of the universe is not enough. It's not a large enough force to pull galaxies apart. Yeah.
I think you consider space as kind of a given in your discussion, this kind of a Newtonian sort of thinking. What about space before the Big Bang?
So I don't have any answers for that. That's a good question.
Excuse me, Adam, how did Hubble first measure how far away the galaxies are?
So I think it was actually a grad student of Hubble's that did it. But
it
was
always.
so using the redshift of these.
No, there is a circular argument because he has to relate distance.
Oh, sorry, yes. So for the local measurements, I think it was parallax for this.
Yeah, but how did they do it?
So just the method of parallax.
Parallax?
Parallax, so it's a method in astronomy for measuring different
I
things.
know what parallax is.
Yeah.
You mean you measure the distance of a galaxy by parallax?
Yes. That's how you measure the distances for local objects. This is not how you measure all distances in astronomy. This is for local measurements. That is one of the methods.
But I heard once that when there is a supernova, then the energy is a constant. That's what
the intensity of the light output is a constant once you normalize it. It's not a constant.
Right. But I heard that was one way. I wonder if
so I'll be talking about supernova.
Hubble already had it.
No, Hubble did not have that. So I'll talk about measurements of supernova in the dark energy lectures because those are important for that. So maybe we'll come back to your question then.
Okay.
Okay? Yes.
Will you be talking about the relationship between the final light scattering and the fact of the 70% dark energy?
Yes. Yes, we definitely will go to that. Yeah. Yes.
When you say that dark energy constitutes 70% of the universe, is that in mass equivalent?
So, yes. So, energy or mass. So it's basically the percentage of composition of the universe. You can view it as an energy equivalent or a mass equivalent. But for the dark energy, it's definitely an energy because we don't associate a negative, so I won't go into the dark energy details now. We don't associate a negative pressure with matter, with mass that we know about. But we do associate, we think dark energy has a negative pressure, so that's why we refer to it as an energy rather than a mass. But we'll go into that a little, that's a little technical. We'll go into that when I talk about dark energy, perhaps. Yeah.
Do we know why photons and electrons resisted the pull of gravity?
So radiation pressure, basically.
Can you speak up? I'm sorry.
Radiation pressure. So the pressure due to the...
Yeah, you said that the photons
Photons,
and photons and electrons seem to resist the pull of gravity.
Yeah.
How could that be?
So it's exactly the same way that a star doesn't collapse in on itself because of gravity. Okay. So stars are
But
stable.
that's yielding to gravity.
No, so if there was no radiation pressure in a star would just collapse on top of itself.
Ah.
Radiation pressure balances the force of gravity, and a star is a stable object because of
So
this.
I see, because the gravity would pull the star into collapse, but the radiation pressure, the inflation, would pull it the opposite way, and so it stabilizes.
Exactly, yeah.
Okay.
Yeah. Yeah.
So, I'd like to ask a question about the light wavelength stretching
Yeah.
and the question of three-dimensionality of the expansion. So the wavelength expansion is a very classical electromagnetic concept. And we measure those pictures are all measured one photon at a time. So if I've listened to a lot of these lectures and I've come to the conclusion that if we have to take the stretching of the wavelength seriously, then that tells me that something about what is a photon, and it has an actual physical meaning to say that a photon has a physical length,
Sure.
a wavelength.
Yeah.
But the expansion is also in the other two dimensions. So if I have a wave surface, let's say I'm on the surface of a sphere a certain distance away from the light source, it's diminishing in intensity by the rule of inverse square, yet I don't understand how that would relate to a photon where you're picking up images one photon at a time when you're detecting that light. So I'm not sure if I'm asking a sensible question, but how does the relationship of expansion of the universe in three dimensions relate to and say something to the layman about what is a photon? And
Sure.
does it have sides, for example?
Yes, so you can think about, so it's really hard to explain what a photon is without showing you the mathematics of it. But a photon, you can think about it as a probability density. Okay, so it does have, you can think about it as a wave, okay, with a physical extent. But once you go into a lab and you try to measure a photon, it depends on the experiment you're doing, right? A photon can sometimes look like a particle, or it can look like a wave. Okay, this is this wave-particle duality. So I'm not going to go into that at all. Okay, but when we talk about using the wavelength of light, right? There's a relationship. There's a mathematical formula between the wavelength of light and the intensity of the light, the energy in that photon that we measure in a pixel in our detector. Okay. And when you write down that mathematical formula, then you can relate the energy that you measure in a pixel in the detector with the wavelength of the light. Okay? And as you measure that intensity as a function of time, you're actually measuring the wavelength of light coming in towards you. Okay? So it's very hard to get into it without showing you the actual mathematical equations, but there is a relationship between the intensity of the photon particle coming in as a function of time and the wavelength of the light from that object.
Can I try to rephrase that question?
Yeah, sure.
When photons stretch, due to redshift, that's the wavelength.
Yeah.
What happens to the amplitude? Does that also stretch?
So the frequency changes as well.
How about the amplitude?
So I don't think the amplitude. The
If it-
amplitude decreases.
But if it's three,
Question, right? Because as the wave fronts spread out laterally,
Yeah.
the intensity at any given location gets diminished by the inverse square law.
Yeah, but
but the universe is expanding sideways as well. So why doesn't the amplitude
So that means
expand?
your probability of detecting that photon in any given place is diminishing because of the expansion laterally. So the wavelength gets stretched, and then the amplitude of the wave gets diminished because it's spreading out over a greater latitude.
But
The
that-
energy
that's
was-
reflected in either yes or no along the wavefront. If the farther you get away on the inverse square law, the only reflection of that expansion is that, like in the Hubble deep field, if you wait, there's a detection, and 6 seconds later there's another one. If I put it over here, a second telescope, I might get one in between. So is it correct then to say that the expansion is reflected in the fact that there is or there isn't the three-dimensional expansion? There is or there isn't a detection.
So what the three-dimensional expansion tells you is that the stretching tells you that the temperature of the photons is going down. That's the stretching of the wavelength. And then the fact that things are spreading out laterally is telling you that the energy density in the radiation is also diluting because of the expansion in the other direction.
And then the expansion also is changing the number of photons that you would expect from these objects which we know are of a certain given intensity. Okay, so these standard candles. Yes?
I understand that you mentioned in the chart about Alpher, Bethe, and Gamow.
Yeah.
Theory. I think that they had absolutely nothing to do with it. I talked to Mr. Gamow about 25 or 30 years ago, and he thought it was a joke. They added Bethe because he wanted alpha, beta, gamma.
Sure, but that paper
He
did.
had absolutely nothing to do with it. Bethe did not know about it.
No,
Never
the joke is that, yeah, Bethe didn't do any of the work in the paper. I put the citation up there because I did want to mention that, but the work in the paper is still valid. The work in the paper is still about the abundances of light elements.
They
The
had
fact that
absolutely nothing to do with it.
no, the fact that Bethe is included in the author list is true, is a joke, but the paper itself is not a joke. Yeah. One last question. Yeah, from you at the back.
Can you tell me, you know, some of the theories of what happened before the Big Bang, or what was the universe?
Okay, so that's a really tricky area. So before the Big Bang, I guess one of the ones I do know about is this notion that before the Big Bang there was another universe. So this is a cyclic universe idea where you have a universe that existed before our own, which went into a big crunch, which caused another singularity, which then expanded into our own universe and another Big Bang. This stuff is kind of real science fiction-y stuff. For me, anyway, I don't work on this area, but I know that these theories are they're out there, but I don't know of any way to test them quite yet. I do know that one of the ideas of this eternal universe, this idea of a universe which keeps going around in a circle of a big crunch and then a Big Bang, one of the predictions for this, so one of the famous people that works on this is Roger Penrose. He had this idea that if a universe existed before our own, you would have black holes in that universe, which perhaps would have evaporated and would have caused ripples that we would see in the CMB of the next universe. Okay, so this is this idea of looking for circles in the CMB. People kind of ridicule this, but you know they were doing legitimate work trying to look for concentric circles in the CMB. But then people did other work, and I think they found Hawkins' initials in the CMB as well, Stephen Hawkins' initials. So it's kind of teaching them a lesson of like, if you go looking for something hard enough, you'll find it. Okay.
Can I just... if anyone is interested...